The section 2 of the chapter 2, Elasticity, is strain. First, let me introduce two terms. One is displacement, which is the difference between the final and initial positions of point trajectory. Strain is a description of the deformation in terms of relative displacement of a part in the body that excludes rigid body motions. Then let us argue the displacement. In this diagram, this red square is the object before deformation, and the red parallelogram is the object after deformation. Let us consider the point A, whose coordinate is x sub 1, x sub 2, x sub 3, and point B, which is expressed using the vector position vector x plus delta x, whose coordinate is x sub 1 plus delta x sub 1, x sub 2 plus delta x sub 2, x3 plus delta x sub 3, equation 2.2.2. Then point A is displaced to point A prime by deformation, and the position of the point A prime is expressed using the position vector A prime, whose coordinate is A prime, A1, A sub 1 prime, A sub 2 prime, A sub 3 prime. Point B is also displaced to point B prime by deformation, and whose position vector is A prime vector plus delta x prime vector and delta x prime vector, whose coordinates whose components are A sub 1 prime plus delta A sub 1 prime, A2 prime plus delta A2 sub prime, delta A sub 2 prime, A3 prime plus delta A3 prime, equation 2.2.4. Please note that the delta x means a vector from here to here is different after deformation from a vector from A to B, A prime to B prime. Then the displacement of point A, which is expressed using the vector u at vector x, is equal to vector x prime minus vector x. Then displacement of the point A is expressed using component u1, u sub 1, u sub 2, u sub 3, and each of component is a function of the position x. This one. Then displacement at B is expressed using vector u at the vector x plus vector delta x, which is equal to vector x prime plus vector delta x prime minus vector x plus delta x vector delta x. Then vector the displacement vector u at x vector x plus vector delta x is also expressed using the component u sub 1, u sub 2, u sub 3, which is a function of position x vector x plus delta vector x. Then difference of the displacement between point A and point B, which is delta vector u, is equal to the vector u at vector x plus delta vector x minus vector u at vector x, which is equal to the derivative of the vector u with respect to vector x times delta vector x. Equation 2.2.7. In this slide, we define the strain tensor. We consider an infinitesimal deformation using this illustration. Let us consider the deformation of this square drawn using gray solid lines. This square deforms into this paralleloid drawn with the dashed black lines. The horizontal axis is x1 and vertical axis is x2. The lower side of this square is rotated by angle alpha by deformation from point A to point A prime. Because the deformation is small, let us assume the sine alpha is nearly equal alpha itself. Then sine alpha, or this angle, is this displacement u2 delta x1 divided by this length delta x1. Then the angle alpha is the limit of the delta x1 into 0 of u2 displacement in x2 direction at x1 plus delta x1 x2 minus u2 x1 x2 divided by delta x1. Then this is equal to the partial derivative of u2 with respect to x1. Equation 2.2.8. Then similarly, the change of the angle from B to B prime is expressed using beta and is equal to the partial derivative of u1 divided by with respect to x2. The angle alpha minus beta divided by 2 is the rotation of this square into this paralleloid during deformation. Here we consider the deformation of the body and do not consider the rotation of the body. Therefore, we subtract alpha minus beta divided by 2 from angle beta and angle alpha. Then we have the alpha plus beta over 2 and in both sides. So angle alpha plus beta divided by 2 expresses the deformation of this square into this paralleloid. Therefore, we define the second rank tensor of the infinitesimal strain epsilon ij as 1 over 2 times the partial derivative of the ui with respect to xj plus the partial derivative of uj with respect to xi, where I and j are coordinate number of the coordinate 1, 2, 3. Obviously, the epsilon ij is equal to epsilon ji. Therefore, the strain tensor is a symmetric tensor. The strain tensor can be expressed using a matrix. The matrix epsilon ij The component is epsilon 11, epsilon 12, epsilon 13, epsilon 21, epsilon 22, epsilon 23, epsilon 31, epsilon 32, epsilon 33. And epsilon 11 is equal to 1 over 2 round u1 over round x1 plus round u1 over round x1. Epsilon 12 is 1 over 2 round u1 over round x2 plus round u2 over round x1. Epsilon 13 is 1 over 2 round u1 over round x3 plus round u3 over round x1, and others are similar. As you can see, the green components are identical because this part and this part are identical, and this part and this part are identical. Thus, epsilon 13 and epsilon 31 are identical, as we have already argued. Similarly, the blue component, epsilon 12 and epsilon 21, are identical, and red components, epsilon 23 and epsilon 32, are identical. The diagonal component, epsilon 11, is 1 over 2 round u1 plus round x2 plus round u1 over round x1. But the first term and second term are identical and divided by 1 over 2. Therefore, epsilon 11 is equal to round u1 over round x1. So epsilon 22 is equal to round u2 over round x2, and epsilon 33 is equal to round u3 over round x3. Equation 2.2.11. Among the strain tensor components, the diagonal components epsilon 11, epsilon 22, epsilon 33 express the expansion or contraction of the body. Let us see this illustration. This is x1 direction, x2 direction, x3 direction. Epsilon 11 express the extension of this pink body into x1 direction by this amount, and epsilon 22 expresses the extension of this pink body into x2 direction, and epsilon 33 expresses the extension of this pink body in the x3 direction. So the normal strains are also referred to as compressional strain. However, in contrast to that name, the plus sign means the expansion of the body. In contrast to the normal strains, the non-diagonal components epsilon 23, epsilon 13, and epsilon 12 express the shear strain. The epsilon 23 is shear strain normal to x1 direction. Epsilon 13 express the shear strain normal to x2 direction, and epsilon 12 expresses the shear strain normal to the x3 direction. As we have seen, the diagonal components represent the compressional strains, whereas the non-diagonal components represent the shear strains. By coordinate transformation, the strain tensor can be diagonalized. namely by finding appropriate translation matrix A, the strain tensor matrix epsilon ij can be written diagonal matrix. Since the strain tensor is symmetric, the characteristic vectors are orthogonal to each other. Therefore, the strains containing both expansion, contraction, and shear can be considered as the combination of a compression and a contraction without shear in right angles with each other. This figure expressed such a case. This square drawn by blue dot lines deformed into this diamond with solid red lines. The coordinate before deformation is expressed using x1 and x2. But if we define the coordinate x1 prime and x2 prime, the deformation can be considered as an expansion in the x1 direction and contraction in x2 prime direction. Then the sum of the diagonal component is referred to as dilatation and expresses the relative volume change. Namely, the volume change over the normalized by the volume is equal to epsilon 11 plus epsilon 22 plus epsilon 33. Equation 2.2.13. Then finally, let us define the normal and shear strengths in the primary ways. So the normal or compressional strain epsilon is defined using this illustration. X0 is original length and it extended in the via delta x. Then normal strain is epsilon equal delta x over x0. The shear strain gamma is defined in this way. So that this is the length of the object body in the y direction, and it deforms in the x direction by delta x. Then the shear strain gamma is defined as delta x over y0. And the angle of this inclination, theta, is arctangent of the shear strain gamma. So this is the end of the chapter 2, elasticity, section 2, strain.